So NASA proved that a 1/6 scale lander drops on Earth simulates a full-scale lander on the moon. They tested that with the Apollo, and that worked great, so we're doing the same thing. This is the Griffin lander, and our 1/6 scale model of it has the same, approximately the same weight and center of mass. So the tests we conducted were plywood on plywood versus regolith, rock, dropping one leg on a rock, the other legs on sand, and dropping on slope. So for the plywood versus regolith, we were basically testing the honeycomb inserts inside the legs to see how much the honeycombs would absorb the crush energy of the impact. So this was our plywood test, covered in a bit of cloth. And the lander does jump a bit, but that's because the plywood is so very strong and hard. So then we did sand. At first we made a mistake because we didn't flatten sand everywhere. So it just dipped into some of the sand and pushed it aside, so we saw very little crush. Then we made a flat surface of sand, and we saw a more significant amount of crush. So that's the initial height, simulant, and plywood. So the results we got from this test were as expected, and it proved that our honeycomb inserts were working well. Now the rock test was rather interesting, as we were landing just one leg on a rock, and what ends up happening is the leg that hits the rock first doesn't compress very much, but the leg that's furthest from the rock absorbs most of the energy of impact as it rotates, as it changes the motion to rotational motion and crushes the far leg. So we did that with two different types of honeycomb, the 5G honeycomb and the 10G honeycomb. There was a premature drop due to some oscillations, but we got it working after the second trial. So that's how much it crushed on the 5G. I think it crushed about a third less on the 10G. Which is good, because 10G is our worst case scenario. So after the rock test, we went on to do some slope testing to find out when the lander would tip over and on what type of slope. So we did high friction slope tests and low friction slope tests. The low friction slope tests were just on carpet without any tape, because we put tape on the underside and it stuck better. So with low friction, the lander slides instead of getting caught and tipping over. We tried foam to increase the friction, but it didn't really work that well. So we tried a foam trap to catch one of the legs upon landing and have it tip over, but that was still difficult at 22 degrees. So we did some simulations to find out approximately where we want it to tip over, and we found it would be it would start tipping at 25 degrees, so we used this 30-degree slope to double check. But this is too low friction, so we had to take the bottom of the legs. We also did testing on moving simulant. You can't really see the simulant, but what happens is the sand disperses as it lands in and it just slides down the slope. So this is with tape. So unfortunately, well, fortunately actually, this is unrealistic on the moon, as there is no way you're going to get such high friction between your lander and the sloped surface. But we want to see what the critical limits of a tip over would be. So in fact, the 1-2-1 configuration of the legs is more stable than the four-legged landing vertically and straight on the same slope. So that was the surprise. This is 24 degrees. We want it to just barely not tip over. And then at 25 degrees, it'll do the same thing, except for it'll hit the critical moment and tip over. Right, so. And the scaled lander was perfectly fine. It didn't incur any damages. So I just wanted to show a quick video of the simulations we did to to check that our simulation software was matching well with the actual results. So this is 24 degrees at the same drop velocity. And this is 25 degrees. 25 degrees it actually tips, whereas 24 it doesn't. And that's the only thing that changed. So the simulation works great, which is good. So conclusion, no tip. At 30 degrees, 2.8 meters per second and low friction, which there's not likely to be extremely high friction on the moon, because our friction coefficient was above 0.75, which is pretty large. And then no crush on sand hills or slopes as the GRC1 simulator we're using dispersed upon landing. And it tips at 25 degrees with 2.8 meters per second and high friction of slightly above 0.75. So on top of doing some drop testing, we had drop rig problems with oscillations. So we added tension supports, and the tension supports ended up working quite well. And remove the uncertainty when you're doing horizontal drops. Because this is without tension support and horizontal drop. So it kind of shifts backwards and then drops at the wrong time. So with tension supports, we were able to eliminate that. It's a little hard to see them, but they are there to exist. And it drops exactly at the time we want at the end of the rotation. And that worked out well. So further testing, the stability of the landing gear is well confirmed. The structural integrity is uncertain at this point because it's a little difficult to test the structural integrity with the 1/6 scale model, as the legs would react a little bit differently and the way things work. And so we are considering doing a project to make an entire leg as possible, full scale, or seeing what else we can come up with for confirming structural integrity of the landing gear. Any questions?
So you've gone a long way towards evaluating conditions where the lander would flip, but obviously, we're not going to land on plywood and at a high angle, right?
Mm.
So at a high angle, you don't really know what the conditions are that we care about, right? Some of them, right?
Yeah.
You've got a good model.
Yeah.
So are there tests that you are going to do that show the cases that we would actually like to avoid? It seems like, so if you're landing on sand, for instance,
Yeah.
on a 24-degree slope,
Yes.
which obviously we would try to avoid, but
Thanks.
you'd like to know what the conditions are where you actually.
So we did land sand on a 22-degree slope, and we could continue to land on other slopes. But the point of doing the carpet testing was to show that unless you have high friction, you're not going to tip over the lander. It does depend also how far the tip would be catastrophic for the lander.
Right.
But that can be easily simulated via the simulation, which can control the friction coefficient and center of mass, everything.
So the the typical case for rollover
Yeah,
is to slide into a trap, like you
yeah,
showed. I think it would be really cool if you did a test where you landed in the sand bin that's significantly sloped and set up a trap and ask how far do you have to slide, what slope matters there. And you may do that in simulation, I don't know, but that would be a great experiment to show.
we will definitely explore a little more on that. We did do one, in the video you can't tell very clearly, but it slides a bit because it's not very far from the edge. Then it hits the edge of the box and just stops. Now to continue doing tests on different slopes and different distances of up the trap would be a great